electronics. Today we are going to discuss PN junction in forward bias. Let us see how the device will behave. See, PN junction in forward bias means like already in the last session we studied about the semiconductor diode, what we are calling it as a PN junction diode. Once PN junction forms, there is no charge carrier transformation is allowed across the junction and the material behaves as insulator. Now, if I want conduction, definitely I have to go for the bias. Bias is nothing but applying additional external energy to the device to get charge carrier transformation. Otherwise, in other words, to mobilize charge carriers in the device. Once the charge carrier mobility is there, then the charge transformation will happen. We know that I is equal to Q by T, the moment of charge per unit time. Then only we can say there is a conduction in the device. So that if we want to get conduction in the PN junction diode, so that definitely we have to apply a bias. That is forward bias. What is meant by forward bias? Forward bias is nothing but applying similar polarities. See, so bias means nothing but we are applying external energy to the device. So external supply, what we are calling it as external supply. So external, what we are supplying to the device? From the positive terminal, holes will be supplied to the material, and the negative terminal, electrons will supply to the material. This is what we are calling it as bias. Bias is nothing but additional external supply. So we are supplying holes and electrons into the device. We know that p-type material, majority of charge carriers are holes, so that the behavior of the device is positive, so that we are supplying holes to the material, p-type material. And similarly, n-type material is supplied with the electrons, so that we are treating it as a similar concentrations. We are supplying similar concentrations. See, majority of holes are holes in the p-type material. It will gives the positive type behavior to the p-type material. P-type material means what? The positive type extrinsic semiconductor. Majority of charge carriers are holes. Therefore, the behavior of the device, that material is positive. Okay, and the negative n-type means negative type. N-type means negative type external semiconductor. Let us see how it will and how the device will respond. See, we know that there forms a junction whenever p-type and n-type metal is added, and we know that the majority of charge carriers are holes in the p-type. That means the number of holes are greater than number of electrons. In n-type, majority of charge carriers are electrons, minority of holes means the number of electrons are greater than number of holes. Now I am applying positive type of external supply to p-type and n-type to negative supply. So this is forward bias voltage applied between forward voltage. So from the positive terminal there will be a supply of holes into p-type material. From the negative terminal there will be a supply to n-type material. See, this is a brief version we are discussing, a simple way to understand. Okay, so whenever the holes supplied into p-type material, already p-type material there is a majority of charge carriers are holes. Whenever additional polarity enters into the material, there takes place a repulsion, because the external supply, whatever the hole enters into the p-type material, it will repel the existing hole, so that the repelled hole will try to move towards n-type. So that there is a depletion layer there will be some capacity depletion layer. It can withstand up to a particular level. We can take a small example here. Suppose the depletion layer can withstand for the pressure of a 10 holes and 10 electrons. So that from here, due to the repulsion force, they will create force on the depletion layer because they are trying to move from P to N. And similarly here, the 10 electrons will create a force on the depletion layer other side. They are trying to move towards N to P. And for example, for 1 volt, let us suppose that a 10 holes and 10 electrons are supplied to the device. For 2 volts similarly, accordingly 20, 20. 3 volts 30, 30. So let us let us assume that the depletion layer can withstand up to the pressure of 10 volts and 10 electrons moving from P to N and N to P. So now I started a 0 volt. There is no supply of holes and electrons takes place into the device. There is no conduction, there is no movement of charge carrier occurred. So next I applied 1 volt. I applied 1 volt. For 1 volt, according to our assumption, 10 volts and 10 electrons are supplied to the device. So that 10 volts will create a pressure on the depletion layer, and here 10 electrons will create a pressure on the depletion layer of the other edge. So that depletion layer can withstand up to the 10 volts and 10 electron pressure, so that it won't allow any charge carrier transformation across the junction. Whenever I apply 2 volts, there will be a supply of 20 holes and 20 electrons, so that the 10 holes will be stopped by the depletion layer, and the remaining additional 10 holes will cross the junction and they will move towards N type, and the 10 electrons will move from N to P, and the collected holes here are attracted by the negative terminal and get neutralized, and the collected electrons are attracted by the positive terminal of the external supply and gets neutralized, so that there will be a charge carrier moment occurs towards positive terminal and negative terminal. So therefore, we can say there is a finite current I arises, so that we can say there is a conduction. Simply, if we can draw a graph between these actions by taking voltage on x-axis, current on y-axis. For the 0 volts, there is no conduction. For 10 volts, there is no conduction. For 20 amperes, there will be conduction. So, if you increase the voltage here, if you apply 3 volts, 20 volts and 20 electrons, the current increases. And next 4 volts, again the current increases. As you are increasing the input voltage, the current also increases proportionally, so that you can mark the graph like after the 10 you can get the increment in the forward bias. So that this is the characteristics. What we are saying, it is a characteristic. Characteristic means the behavior of the device. So we are analyzing or calculating the behavior of the device by varying the voltage, how current varies in the device. That is what VI characteristics we will say. Okay, so this is the working and characteristic graph of a PN junction diode in a simplest way in forward bias. Okay, if you like this video, please like and subscribe to my channel, and we will discuss several topics in electronics.